so what are the limits to parallel processing? Well, one could be, you couldn't put more cores on a single chip. That would be a possibility. Maybe the interconnect is not high performance enough. Maybe the DRAM is not high performance enough. And I don't really know what is going to be the limit. Right? And partly also depends on the workload. So I think I would just push in all directions, see where the limit actually is reached, and once the limit is reached, try to find another way to push. And next to me it says quantum computing, and a number of people ask me about quantum computing today, so maybe I'll sort of answer that question right immediately. That's it. Quantum computing looks interesting, has a lot of promise, but I think it has a really long way to go before we're going to see any real quantum computers that we can actually use and run real computations on. So my bet is for a while to come on current technology and see where we go. And maybe we'll run into a limit by the time quantum computer is real.
Okay, so you already answered the second question, which was about quantum computation.
Oh, good, I got 2 in 1.
Okay, so here is another one. Can't we make single processors more powerful? What prevents us from doing that?
Energy. So you cannot push up the clock speed, and so you cannot run the digital circuits faster. So then you could think about using more transistors to improve the number of instructions per clock tick, basically, if you will, which is called ILP. And it looks like, basically we don't know how to improve that further because there's not enough micro-parallelism available to actually get that better performance. So that's the...
Okay, and here's another one. It's an interesting one. Is it possible to upgrade a processor without reinstalling the OS?
Not that I know of. I mean, what do you mean with reinstalling the OS? You can certainly upgrade the processor, correct? You can take your machine, put it down, switch out the processor, and start running again. So that's certainly possible. If you mean, changing the processor while the operating is still running, that seems hard, isn't it?
Okay, and this is the last one I'm going to read for you. Actually, there are many more, but let me just read one more. What is the future of AMD's accelerated processing units compared to today's CPUs? Will they replace CPUs?
Yeah, that's an interesting question. Again, I don't know what the answer is. Clearly, the accelerator processors are going to be important, and you will see, I think, you'll see them as part of the processors more and more often, which introduces actually interesting programming problems about how you divide the work between the specialized processors and the general purpose processors. But I don't really know the answer. I mean, in fact, that's a very excellent research question to investigate. My general feeling, though, and this is unsubstantiated, and so I could be totally wrong in this, is that the general purpose processors are going to be more dominant. I think it's easier to stamp out many similar processors than actually on a single chip, than actually having a lot of diversity on the chip. So I would go vote for uniformity as the future, but I could be completely wrong about that.
Okay, and maybe here is another one, since you are answering so fast, so maybe I will ask another one. It's one thing to program a sequential computer and another thing to program a parallel computer. It's much more difficult. So is there a solution around the corner that you can see?
No, I don't think there's a solution around the corner, at least not that I know of. I think it's going to be one of the challenges going forward is trying to help people make parallel programming easier. And with some of the, if you start doing lock-free concurrent data structure programming, it's going to be even harder. And so solutions to simplify programming, I think, is going to be is a great research direction. And of course, there's a number of proposals in that direction, and we have had some successes. You can think about MapReduce as a tremendous success in making parallel programming easier because the programmer doesn't have to think about parallel programming at all. Unfortunately, of course, it has a limited application domain. And so an interesting question is, are there other examples like that that could simplify parallel programming for a particular domain tremendously? And it'd be good to have ideas there.
Okay, thanks.
Thank you.
So Franz, if you want to leave. Okay, so now I'm going to do it in round robin. I will ask one question for each of them. Okay, we got the most number of questions for Rick. Unfortunately, Rick is not here. And I had to discard a lot of them, sorry, because they were asking how Microsoft recruits, hires, and all these kinds of things, which are very valid questions, but I don't think this is the place where we need to answer those questions. The answers are much more easily available. So, and some questions that I cannot ask Anandan as a replacement for Rick are questions like, if there was a doomsday and you had to choose only one technology, what would be that? Now, naturally, Anandan's answer and Rick's answer need not match. So, I can't ask Anandan as a proxy for those. But the questions which I think, Anandan can very well answer. So, here is one. How Microsoft is working on research problems which seem to be purely academic in nature?
I assume the question is, how is it that we are doing that? Yeah, so when, it's a research model. Our research model, I think Rick explained it a little bit, is to let people choose what problem they work on. And, so there may be many problems many people will work on. And then out of which, some of which may have immediate application, some of which have applications maybe 5, 10 years, some of which may be entirely futuristic, and that's fine. But if we limit what they do by directing them, then we'll limit their thinking, and that's really not a good idea. So we have it as a matter of principle to allow researchers to explore the frontiers of ideas on their own, but there's obviously always enough that we can actually leverage that it makes it for exciting, and that way it takes us in new directions, right? Rather than us limiting the directions in which people go.
Okay. So next question I will ask Professor Narendra Ahuja. There are two questions that are related, so I will ask together. The first one is it possible for normal private engineering colleges and MTech students and faculties to join ITRA? And the second is, how will the ITRA program reach students who do not study in urban areas?
The answer to the first question is a very definite yes. In fact, there are already many private colleges that are participating in the sense that they are writing the proposals that would be considered like any other proposal. So the answer is definite. Yes, in fact, we are counting on that because there are more private colleges coming up, at least as many private colleges coming up as the non-private colleges. So yes. The second is
rural areas.
Rural areas, you will really need to hook up with some college. I mean, currently the mode of functioning is that the ITRA is interlinking the colleges, institutions, as opposed to students. So the student-college connection will have to be, at this point, done by you, by the student. And once you are there, then the institution will at some point get into the network. If your college gets into the network first, earlier, because they are already quite, remember that there is a quality gradient in the pyramid. The most accomplished institutions are the early entrants, and then gradually more and more colleges join in. So depending upon where you enter in the network, if you are starting at a college that gets into the network sooner, then you will be in sooner. So the answer is you get hooked up with the college and the rest will take care of itself.
Okay, so the next question is for Ravi. Is there a convergence between machine learning, graph theory, and linear algebra? Do you see IR as a potential area where all these three are converging to, means applied to?
Yeah, that is a good question. Indeed, the machine learning crowd is, a very happy lot because they're able to solve all problems, whereas the theoreticians try to work on the worst case, and then they get stuck because the worst case is always hard. So, in some sense, understanding why machine learning is successful, what is the class of problems or the model of problems that they can actually solve is the first step, I think, in this convergence. Once you figure that out, maybe you can extend the class quite a bit rigorously to sort of get the advantage theoretically applied to all areas that machine learning is successful in so far. IR might be a good example. I think it is, in fact, a good example where linear algebra is used a lot, but there are a lot of other areas where this combination might be very successful.
Okay, so here are two questions for Professor Ikwechi. Both are related actually. So one question says, in case of Konark Sun Temple, which is in Orissa, India, most of the sculptures are already destroyed. The other question is related. It says, in Harappa and Mohenjo-daro, cities, there is the Bronze Age civilizations, and also most of the things are destroyed. So we have only the ruins. Is it possible by using this cyber architecture and computer vision techniques that we reconstruct those cities or those sculptures?
That's my dream. And actually, at the second segment of e-heritage project, I show some of the mixed reality tour. And that mixed reality tour is basically targeting such areas. There is nothing existing besides ruins. And however, in order to create images, we need literature survey and other technique. And I skipped some of the segment, but what I did was we digitized, in Japan, there is a Buddha called Nara Big Buddha. And people believe that is 6th century, but that reality was 16th centuries. And however, 6th century dimension existing. So by using computer graphics tech, first we digitize current Big Buddha, and based on the literature data, we modify by using computer graphics technique and regenerate it. So yes, possible.
That's very nice to know. So again, a question for Anandan. Again, this also has been asked by a lot of people. Is PhD compulsory for doing research in Microsoft, or I guess in general research?
In a strict sense, of course, PhD is just a degree and therefore not compulsory for doing research, and there are people who don't do PhDs, do research. However, the PhD process, that's something in the process of training and research which you don't get anywhere else. See, when you study bachelor's or master's, you're learning specific subjects. You're learning linear algebra, vector calculus, or electromagnetic fields, or whatever the subject is, you are taught what is known in that subject. When you go to PhD, you are no longer in that position because the subject you're studying is a problem for which there does not exist a solution, or if there exists a solution, the solution is obviously not good enough, otherwise you would not be working on that problem. So you begin to reshape the problem, you begin to ask the questions. I think Professor Ahuja mentioned in his talk, the first thing you learn when you do research is not how to solve a problem, rather how to formulate a problem. Well, actually it's the last thing you do when you do your PhD because it's a little bit hard to figure it out. First you solve problems that are known, but then once you figure out how to formulate a problem, that's when you're ready to get a PhD. And this is a nice time because you're not burdened with producing something or delivering something. You don't have any other constraints. You are simply there to learn how to do research. And it is still a process of education. And there's no other place you can get that type of training, other than in a PhD education. So yes, it's really, really important to do that. Of course, you can do research without doing it, but we always find that people who have had the PhD experience are a lot better starting out as researchers.
Okay, so the next question is for Professor Ahuja. What is the evaluation procedure for participating institutions in ITRA, especially the mentees?
The evaluation procedure is for the proposals that come out to ITRA. So for example, let's consider the mobile RFP. So there will be a proposal coming, let's say from a team. The proposal will be from the team. The proposal will be evaluated as a document, not directly worrying about the team members. So the proposal is being written by a team, and the team together decides the quality of what goes out. Now, in that team, there will be, even during the writing process, there will be learning. There will be some institutions in the team whose strengths will be one subset, another set of institutions will have different set of skills. So together they will come and put together a document that not only combines their strengths, but also in the process, there is cross-diffusion of the strength. So those who are weak in something learn it from the next institution and vice versa. So the evaluation process would be for the entire proposal. Now, when you form the teams, when the institutions come together to form a team, clearly it's important that there not be large disparity between them, because then it becomes a very difficult and not as pleasant a process. if there is a gap. So it should be remembered that when A, B, and C come together, that there is a differential relationship between them in terms of their existing quality, so that the pyramid eventually has a rather slow quality gradient from top to bottom, negative gradient. So yeah, bring together institutions that are very similar in strengths or quality.
Okay, so the next question is for Ravi. It's an interesting one. It's very hard to think in even 4 dimensions and visualize things. Then how can we think about what happens in 1,000 dimensions? How do you work with them?
Well, that's a good question. I think you have to think less in 1,000 dimensions than in 4. That's a nice part. Because basically, the law of large dimensions, which I sort of put up the phrase, is like the law of large numbers. Once you have large number of things independently doing something, on the whole, they behave like the average should be. And the average is a much easier quantity to understand. So if you're sitting in 1,000 dimensions, if you're collecting data with thousands of features, probably a lot of the features are either unnecessary or depend on other features. But in any case, it doesn't act, I mean, it's not as if the data actually lives in 1,000-dimensional space. Your job is to figure out the 4-dimensional or the 6-dimensional subspace it lies in, and that's why it makes it easier.
Okay. And one more question for Professor Ikeuchi. It's a short one, actually. How much time did it take to build the cyber model for the Bion Temple in Cambodia?
Well, unfortunately, 5 years. But, I think, next target is a rapid prototyping. So, maybe, yeah, well, unfortunately, 5 years.
So did the student not get his PhD for those 5 years?
No. That, project consists around 5 to 10 PhD students, actually.
Okay, so let's thank them again. Unfortunately, we don't have any more time to ask questions, but there are lots. I will